functions? Because you mentioned the Fourier transform.
Yes, they are related to bound functions, and they are related to some kind of de Gennes operator, this famous operator, but not with Neumann conditions, but with a condition depending itself on the Fourier parameter. So
Okay,
this is
so strange, weird.
I could ask a question as well.
Yes, please.
Yeah. Yes. First, I apologize for not referring during my talk to your Pauli paper. It was in my manuscript by.
Oh, it's a scandal! It's a
I
scandal.
was in a hurry in the end. But your big constant in front of this exponential term. I mean, for the Pauli operator in this Aronoff-Kashe theorem, you see this flux of the magnetic field, and there is nothing of that sort here, right? So this is completely different.
Yes, it's. I would say yes. It's completely different.
Yes.
But somehow it's an for the Dirichlet-Pauli for the Dirichlet-Pauli case. Somehow the semi-classical limit can also be seen as a large domain limit.
Yes.
In principle, in the end, we end up with this Aronoff-Kashe theorem somehow.
Okay. I don't see how, but okay.
Yes.
Yeah.
Okay. So thank you again, Nicola, for your talk. And I think we can pass to the next speaker. So there is still a couple of minutes to wait, but well, Siamak, you can just share the screen to be sure that everything works, and we wait a few minutes before start. Wonderful. Maybe you
can you see my screen?
Yes, it works. Maybe you can put it to full screen.
Yeah, sure.
Okay, wonderful.
Okay. And if I change it, you can see.
Yeah,
right?
it's okay. Everything is fine. So let's wait a couple of minutes and then we'll start. Probably I think we can start. So just an introduction of the next speaker, who is Siamak Taati from American University of Beirut, so local speaker finally, and he's going to speak about quasi-crystal phases in a finite range lattice gas model. So please.
Yes, thank you. So let me start by thanking the organizers for inviting me to talk in this beautiful conference. Yeah, so the topic and the kind of techniques that I will be using, I suppose it will be kind of different from what most people are used to, but I hope that I will be able to convey some message and you benefit at least a little bit from this talk. Okay, yeah, so I will be talking about the statistical mechanics of quasicrystals. So there is this big problem in statistical physics, namely the crystallization problem, that we want to understand why is it that most material when we lower the temperature, they take crystalline form. And so we want to be able to construct some model with a reasonable interaction, which has crystalline form at low temperature. And furthermore, we want to be able to explain why is it that such crystalline phases are so widespread. So that means that the explanation should be quite robust, that with respect to the details of the model and the details of the interaction. Then there's you can call it a sub-problem of the crystallization problem, namely the quasicrystal problem. And here we want to explain the stability of quasicrystals at positive temperature, at non-zero temperature. And here, even if you are able to find some abstract model, an abstract model of a quasicrystal, some abstract model which has quasicrystal phases, that would be already quite interesting. So notice that, I mean, the crystallization problem, of course, is a problem in the continuum. So in the lattice model, in the context of lattice models, it would not be very interesting because the main point is being able to explain the emergence of this periodic order. Whereas in the quasicrystal problem, even in the context of lattice models, there's something completely non-trivial. So you can start by attacking the problem in the context of lattice models. And that's what we want to do. So we want to construct a model of a quasicrystal, a lattice gas model of a quasicrystal. Okay, so this is some picture slide. So the quasicrystals are a certain type of material that physicists, I think in the 80s, I'm not sure when exactly they discovered. So here on the right, we have the diffraction pattern of a quasicrystal. And if, as you see, first of all, it's very, very highly ordered. But on the other hand, if you see, it seems that there is a tenfold symmetry. So if you rotate the diffraction pattern by 1/10 of an entire row, 1/10 of 2 pi, you get something which is the same. But on the other hand, mathematically, we know that the 5-fold symmetry, so this is, here we have 10-fold symmetry, in particular, 5-fold rotational symmetry. 5-fold rotational symmetry is not consistent with translational order, translational symmetry. So if you have some pattern which is periodic, we know that it can have only, so the rotational symmetries that it can have are limited to 2-fold symmetry, 3-fold symmetry, 4-fold symmetry, and 6-fold symmetry. So in particular, you cannot have 5-fold symmetry. And so that means that although from the diffraction pattern, it's clear that the structure of this material is highly ordered, the structure is not periodic. And so that is an example of a quasicrystal, what people call quasicrystal. So in the language, I think so this is what quasicrystals are. So we have long-range orientational order, but we don't have any translational order. I suppose this is the definition that physicists would use for quasicrystal. Okay, so now the problem that I want to tackle is more abstract. So I want to construct a lattice gas model with finite range interactions, which has quasicrystal phases at positive temperature. Okay, so I think I can, I mean, everybody here is an expert. I can skip this slide. But let me just very quickly review in the context of lattice cache models. So in lattice cache model, we have, the system consists of components, identical components, which are arranged on an infinite lattice. So let's say the two-dimensional square lattice. And a classic example is the Ising model. And each component has finitely many possible states. And in the case of the Ising model, each component is either upward or downward. So you can imagine that these are magnets which are either upward or downward. And the interaction between these components are modeled by energies, interaction energies. So to each finite pattern of states, there is an associated energy. In the case of the Ising model, the associated energies are non-zero only for neighboring sites. And the energy is -1 if the two neighboring sites are aligned. So that means the two magnets are aligned to each other. And +1 if the magnets are anti-aligned. Yeah, so then the one very interesting and important idea in statistical physics is that the macroscopic states of a system can be understood as probability measures on the space of all microscopic configurations. And in particular, Gibbs' hypothesis is that the macroscopic in thermal equilibrium are adequately described by the so-called Gibbs measures. And what are Gibbs measures? So Gibbs measure, you can imagine it as the distribution of a random configuration, which has this property, satisfies this equality. And this equality essentially is what it says is that if I take any finite region in the lattice, the distribution of this lattice, the pattern that I see in this lattice in this region, conditioned on what I see outside, is the Boltzmann distribution. It's a Boltzmann distribution associated to this notion of energy that we had. And there's a factor minus beta, and beta is just the inverse of the temperature. So in particular, when the temperature is high, it means the beta is very small. So this the exponent is close to 0, and in particular, that means that essentially everything is independent. So all configurations have more or less the same weight. Everything is independent. Whereas if temperature is low, beta is very high. So the configurations which have lower energy are given much higher weight compared to the configurations which have higher energy. Okay, so some basic facts about Gibbs measures. First of all, under very general conditions, Gibbs measures always exist, and they form a simplex. First of all, they are not necessarily unique, and this is a very important idea in statistical physics that so since this equation, the definition of Gibbs measures is only in terms of the conditional probabilities, it doesn't necessarily uniquely determine the Gibbs measure. And the non-uniqueness is important because it corresponds to phase transitions. Okay, so the set of Gibbs measures at a given temperature form a simplex, and the extremal points of this simplex are the ones that physically we should interpret as the macroscopic phases of the material or of the system. Well, there's some justification for that, why we should consider the extremal points and not the points inside in the interior of the simplex. Okay, so let me again review what is known about the Ising model. So this, because it clarifies the kind of things that I will be talking about later. So in the case of the Ising models, again, there are two possible states per side, either upward or downward. Downward here is denoted by blue and upward by yellow, but there's symmetry. So at high temperatures, meaning that beta is smaller than a critical value, there's exactly one Gibbs measure. And whereas at low temperatures, meaning beta larger than the critical value, you can show that there are exactly two extremal Gibbs measures. And so one of the extremal Gibbs measures is concentrated on configurations which look like this. So there is a sea of blue, so a sea of downward spins, magnets, and then there are occasional islands of yellow. And the other measure is just a symmetric the version of this. So the sea of yellow, and then there are small islands of blue. Yeah, so let me emphasize that there is this sea island picture here, that there for the extremal Gibbs measures at low temperature, one of the two states essentially percolates. So here in this example, in this figure, the blue state percolates, whereas the other color does not percolate, and it forms these finite islands. Okay, so this is the kind of model that I'm interested in. And now I want to construct a different model, perhaps with more states per side and a different finite range interaction energies, which has quasicrystal phases. So here there are two types of phases. So at high temperatures we have a disordered phase, and at low temperature we have an ordered phase, but it's very highly periodic. So now what I want is a quasicrystal phase at positive temperatures, sufficiently low positive temperature. So what do we mean by quasicrystal phase? So the guide is the physicist definition, which is some phase which has long range order but no translational order. But now the question is, what do we mean exactly mathematically by long range order, and what do we mean by translational order? There are some answers to this, but on the other hand, so since I want to just construct one example, I don't really need to have a perfect definition. So a perfect definition is needed if I want to know exactly when when my model is a quasicrystal and when my model is not a quasicrystal. But here I just want to say that my model is a quasicrystal. So it's only sufficient that as long as it satisfies certain features that warrant the definition of warrant the name of the title of quasicrystal, that would be sufficient, and that would be enough. So it's not so the conditions that this model will have or phase will have do not need to be necessary for the definition of quasicrystal. Okay, but yeah, so let me talk a little bit about aperiodic tiles. So I think since the very beginning of the discovery of quasicrystals, it was recognized that there is some connection between quasicrystals and aperiodic tilings. And aperiodic tilings, even before the discovery of quasicrystals, they had been discovered by mathematicians, and they were being studied. So now I want to talk about a little bit about a particular type of aperiodic, non-periodic tilings. So namely aperiodic Wang tiles. So what is a Wang tile? So you can just imagine that it's we have these identical square tiles, and the edges are colored. These are my tiles, and the edges are colored, and the colors just indicate which tiles can be placed next to which tiles. If, for example, on the right of this first tile, I can only place a tile which has a green on the left. So in particular, for example, this one can be placed on the right of this tile. So this is my rule of tiling. And the objective is that we want to tile the entire two-dimensional plane. But yeah, so here is an example of a tiling of a certain region of the plane. Now the interesting fact is that there are certain tile sets of finite sets of Wang tiles that are aperiodic, meaning that first of all we can use them to tile the entire plane, but on the other hand, none of the tilings that we can make with these tiles are periodic. Okay, so this is what I call what we call an aperiodic set of Wang tiles. Now, an aperiodic set of Wang tiles, you can imagine it as a quasicrystal at 0 temperature. Now, what do I mean by this? So let's say I have an aperiodic set of Wang tiles. Now, let's say we associate energy +1 to each tiling error. So for example, here, so in this particular configuration, there's a tiling error here. So these two tiles do not match. So I assign energy +1 to this pattern. Here again, there's an error. I assign energy +1, and the rest of the neighboring sites are all correct. So the energy of this particular region of the space is 3. Okay, so now if I have this energy, so that I have a lattice gas model. So the ground configuration are non-periodic for this model. So, but what I call a ground configuration is a configuration whose energy cannot be decreased by modifying a finite number of positions. The ground configurations, you can show that they are all non-periodic. They do not need to be perfect valid tilings. So what most of them are valid tilings, some of them are just valid tilings with some lines of defects. But they're essentially valid tilings. Whereas the ground states, so here, I mean, the terminology is not standard. What I call a ground state is the accumulation point of Gibbs measures when we lower the temperature to 0. So any accumulation point of Gibbs measures as we lower the temperature to 0, I call a ground state. So the ground states are supported at ground configurations, which is general fact. So in other words, we can think of this aperiodic tile set as so it's something which has long range at 0 temperature. It has long range order, but the order is not orientational. So it's not translational. Okay, so now so here is a different version of the original problem. So we want to construct an aperiodic tile set and a suitable finite range interaction, perhaps a different interaction than this one. This one was very simple, just assigning energy +1 to errors. So perhaps more complicated interaction, which has such that all non-periodic, all or some of the non-periodic tilings are stable at positive temperature. And what do I mean by stability at positive temperature? So what we mean is that if, well, in general, what do I call a stable ground configuration is a ground configuration that at sufficiently low temperature, there is some Gibbs measure which can be thought of as a perturbation of that ground configuration, that particular configuration. So you can think of it as that ground configuration together with some thermal fluctuations. But still, I mean, it's not clear what do we mean exactly by perturbation. There are different answers, different mathematical answers to this. So one possibility would be closeness in a weak topology, but that's not very good. That would be very weak. It would be not strong enough to. And but I think the strongest and most interesting one is having a sea island picture. So that the Gibbs measures should have this sea island picture, meaning that we have a sea of sites which agree with the ground configuration, and then there are small finite islands of error or faults. Okay, so now here is the result that I want to talk about. So this was just introduction. So here's what I want to talk about. It's a particular construction of a lattice gas model, a 4-dimensional model. It's not ideal, but it's a 4-dimensional model, and it has finite range interactions. Each site can have 17 possible states. So you can think of 16 of them as 16 types of particles and one of them as blank. And these 16 particles, they form an aperiodic tile set. Okay, they form an aperiodic tile set along two directions of two of these 4 dimensions. And the property that we have is that configurations that form valid tilings along these 2 dimensions, and they're constant along the other 2 directions, are strongly stable, meaning that they have at sufficiently low temperature, they satisfy these. There are Gibbs measures which satisfy the sea island picture. Okay, so this is what we want to construct. So let me just give you some remarks. First of all, the interactions are really finite range. The range is very small. So the energy is assigned only to patterns which can be fit into 2 by 2 by 2 by 2 hypercubes. So all the other patterns, larger patterns, have energy 0. And well, I told you that these configurations are non-periodic in 2 directions, but constant in the other 2 directions. This is not a real limitation, because I can consider 2 copies of this model, and one of them is rotated such that then together these two will be non-periodic in every direction. There's one disadvantage of this model, which is that it admits also non-quasicrystalline phases, non-quasicrystalline Gibbs measures. Okay, so maybe okay, so this is what I already told you. So maybe another way to describe the Gibbs measures that I have for this model at low temperature is that I have ergodic shift invariant Gibbs measures, which are first of all, they are not extremal, so they do not correspond to macroscopic phases. And furthermore, if I take so you remember that this is a simplex, so each Gibbs measure has a extremal decomposition. So these particular ergodic Gibbs measures, in their extremal decomposition, there is no periodic Gibbs measure. So all the extremal components are non-periodic. Okay, so here are some related results. There is this nice result by Van Enter, Mienkiewicz, and Zahradnik. So this is a 3-dimensional model. So it's better, in this sense, it's better than my construction, but the interactions are not finite range. And since their construction was an open question that whether this can be achieved with finite range interactions. So yes, so there's 3-dimensional with infinite range interactions, but exponentially decaying, which has some sort of quasi-crystal ground configuration which are stable at positive temperature. Then there is this construction by Duron, Romashchenko, and Shen, which is a 2-dimensional aperiodic set of Bank tiles, which is stable against small Bernoulli perturbation, Bernoulli noise. So now here, in comparison to what we want is stability against thermal noise, and thermal noise is highly non-independent. So, but this result is really beautiful, and the idea may be used in the future to construct simpler models. Then there is, okay, so maybe I skipped the result of Gatch because, yeah. So then there are all kinds of interesting constructions. So for example, this Chazot and Hoffman, they constructed a 3-dimensional finite range model in which none of the ground states which are shift invariant are even weakly stable, meaning that if I take Gibbs measures, so if you lower the temperature, no choice of the Gibbs measures would converge. So there's a high level of chaotic behavior at 0 temperature. Okay, so the construction that I will be talking, I will explain in more details. Well, essentially it's a collage. So it has 3 components from the theory of cellular automata and tilings. So this is a topic that I'm more of an expert compared to statistical physics. So there are three ingredients from cellular automata and tilings, And essentially, we are putting these together. And it's interesting that it has some interpretation into terms of statistical mechanics. And the three ingredients, so first of all, the first one is that if I have any two-dimensional cellular automata, I can simulate it with it by adding two additional dimensions, so that in this new cellular automata is robust against Bernoulli noise. Then the second component is that there are aperiodic tile sets which are deterministic in some sense in one direction. And the third component is the link with statistical physics, namely that if I have a positive rate probabilistic cellular automaton, then if I look at the space-time diagrams, space-time trajectories, the distribution of those space-time trajectories are Gibbs measures for an associated finite range interaction. Okay, so let me just go one by one and tell you about what are exactly these ingredients. Let me start by cellular automata. Okay, cellular automata are, again, they are models based on these lattice configurations. So they're just discrete time dynamical, certain type of discrete time dynamical systems on the lattice configurations. So let's consider the one-dimensional version. So here I have a one-dimensional lattice, and at each position I have two possible states, blue or red. And so this is the state space of my my dynamical system. Then the transformation of the dynamical system, so transforming one configuration to another, is defined by a local rule, meaning that at each position, I have a local rule which I apply to every position, each single position, to update the color or the state of that position. So for example, here I update the symbol by looking at these 5 neighboring symbols. Here I update it to blue, here I update it to red, here I update it to red, blue, and etc. Okay, so now this gives me a transformation, global transformation of all the configurations. And this is a very nice transformation. It's continuous and it commutes with the translations. So you can study it, and people study it from the point of view of dynamical systems. Now,
sorry, Siamak.
Yes.
So what topology you use to define continuity?
Just a product topology. So for each position, I have discrete topology, and then I can take the product topology. It would be. So with the product topology, you essentially have the counter set. It would be. Okay. Yes. So now, if the local rule is probabilistic, then I get what we call the probabilistic cellular automaton. So at every step, we apply this probabilistic rule at every site. And so there's also an extra condition that we apply it independently at every site. So now we have this transition rule, global transition rule for mapping one configuration to a random configuration. So then we obtain a Markov process, a discrete time Markov process. Okay, so this is also studied in probability theory as nice examples of Markov processes. Now, there's a class of probabilistic cellular automata that come from deterministic cellular automata by adding noise. So let's say I have a deterministic cellular automaton, then at every time step, I first apply the deterministic cellular automaton. Then independently at every site, I add some noise. That would give me a just nice example of a probabilistic cellular automaton, which in some sense it is very close to a deterministic cellular automaton. Okay, so here's an example of a deterministic cellular automaton, which has a very nice property. This was discovered by André Thum in, I think, in 1979 or 1980, something like that. So there are 2 possible states per site, black and white. And the rule is an asymmetric majority. So at every position, we look at these 3. So here, if I want to update this site, I look at the upper side and the side on the right, and I take the majority of these three. So in particular, in this case, in one step, the central cell, this side will be updated to black. And in this case, it will be updated to black again. And here again to black. Okay, so now this has a very nice property that if I have a sea of infinitely many whites, and there's only a finite island of blacks, then after a finite number of steps, all the blacks will disappear. And why is it the case? So this is very simple. So I'm going to illustrate to you. So let's consider a triangle around all the black sides. Now, if I look at these sides, which are to the left of the left edge of this blue triangle, so these are not going to change. The state of these sides are not going to change because the majority is again white. The same way the sides for which are below the blue, below the blue triangle, and also the ones which are above this diagonal edge of the triangle. On the other hand, the ones that are the sides which are inside the triangle along the diagonal, they will be updated to white. So that means that in one step, the triangle, this encircling triangle, will shrink. And then if I repeat this, iterate this, after a finite number of steps, this triangle will disappear. Now, of course, there is a symmetry in this model. So if the same property holds if I have a sea of black and a finite island of whites. Now, the beautiful theorem by André Thom is that there is some sort of stability. So these all black and all white configurations, they have some sort of stability even in presence of noise. So if I have small noise at every time step at every position, so that means that then I would get a probabilistic cellular automaton. Then the trajectory of the all white and the trajectory of the all black are stable against this noise. That means that they will remain close. The trajectory of the all white will remain to all white throughout the evolution of the system, and the trajectory of all black will remain close to itself again. Good. Now, this is one classic result in about the cellular automata. Now, Peter Gatch and John Raef, they discovered that they can use Thom's model to simulate any d-dimensional cellular automaton, any cellular automaton in any dimension, by adding 2 extra dimensions. So simulating a d-dimensional cellular automaton with a d plus 2-dimensional cellular automaton in a way which is resilient against noise, meaning that the trajectories will remain close to the trajectory of the original cellular automaton. So you can recover the trajectory of the original cellular automaton from this simulating cellular automaton, even if there's noise. And the idea is that, so if we start from configuration of the original cellular automaton, then we replicate each symbol in 2 additional dimensions. So replicate every symbol with a plane, which contains copies of that symbol. And now at every time step, we first apply Thom's rule on each of these planes. This would be our error correction stage. And then we apply the d-dimensional cellular automaton along the other d dimensions. Now then essentially it follows from the result of Thom that every trajectory of this cellular automaton, this new cellular automaton, which is well formed, but the initial condition is well formed, meaning that along the 2 extra dimensions, it is constant. So for each of these configurations, the trajectories are stable against noise. Okay, so this was the first ingredient of the construction. What about the second ingredient? So this is about aperiodic tiles, deterministic aperiodic tiles. So let me start with a different type of tiles. So these are geometric tiles. As an example of geometric tiles, so here the tiles do not need to be, they're not square tiles, but they have some geometric shape, and they also have some decorations. And in this case, while for rank tiles, or these square tiles, we were not allowed to rotate or reflect the tiles. Here we are allowed to rotate or reflect the tiles. And so this example was constructed by Robert Amann. And yeah, so now when we want to tile the plane with these tiles, they of course the tiles should geometrically match, but also these decorations should also match. So the blue lines should continue along the blue lines, and red lines should continue along the red lines. Now, these tiles have some sort of self-similarity, meaning that we can combine these tiles to form larger copies of themselves. So these two are essentially, they're isomorphic to the original tiles. So that means we can repeat this over and over, and we get a valid tiling of the entire plane, which is self-similar. But more importantly, any valid tiling, so you can show that any valid tiling of with these tiles, it can be decomposed into these super tiles in a unique way. So yeah, so we can recognize these super tiles in any valid tilings in a unique way. So that means that you cannot have periodic tilings because of this self-similarity, periodicity cannot happen. This was proven by Amann, Grunbaum, and Shepard. Yeah, so now Amann was a very clever guy. Well, I don't know if I don't know if he's alive or not. So notice that if we cut one of these valid tilings along these blue lines in two different directions, we get some sort of not this kind of lozenge tiles. And now if we deform these and symmetrize all of these into squares, then we get something square tiles, which are essentially rank tiles. You can encode them as rank tiles. And here is different color-coded version of those lozenges. And now we have a set of rank tiles which are essentially they are simulating these original tiles. So in particular, this is an aperiodic set of rank tiles. But this set of rank tiles has a nice property, and namely its determinism property. So if it has this property that if I look at the two colors on the top, the way that I have drawn these tiles in sideways. So the two colors on the top uniquely determine the tile. So there is, for example, there is only one tile which has red on top. And there's only one tile which has light blue, dark blue on top in this order. On the left we have light blue, and the right we have dark blue. Well, in fact, this particular tile set is also deterministic from the opposite direction. So the two colors on the bottom also determine uniquely the tile, but we don't care about that. But I mean, this is a very nice and simple example of a deterministic. This is an aperiodic tile set which has this determinism property, but there are all kinds of different constructions which have similar and even stronger properties. For example, there are tile sets aperiodic tile sets which are deterministic in 4 different directions, or even there's a recent construction by Guillaume and Zinoviadis, which is deterministic in all directions except two opposite. So in particular, all real directions except two opposite directions. For the construction that I'm going to talk about, I'm talking about any of these tile sets would work. So but I'm using this one because it's the simplest. Okay, so now there's this idea that from Jarkko Kari that if we have a deterministic tile set, we can build a cellular automaton out of it. It's very simple. So, I mean, of course, Jarkko Kari used this for some very interesting result, but which I'm not going to talk about. But this is the idea that if I have two tiles, so yeah, I'm going to construct a one-dimensional cellular automaton, and it has this rule. The local rule is like this: that if I have two tiles like this, then in the next step, I put in between a tile which matches the two colors on the top. And there's at most one tile which can be placed here. So there's only at most one matching tile here. If there is such a tile, I put it there. And if there's no such tile, then I put blank. So this is a new symbol. Okay, so here is an example. So let's say time goes downwards. So I start from this this configuration, this one-dimensional configuration. After one step, I have this configuration. So I have just placed tiles, the unique tiles that match the colors on the above. And then maybe after 3 steps or 4 steps, there is this position which there is no matching tile. So I place blank. And then afterwards, the blank symbol will spread. Okay. So now this cellular automaton has the property that all the bi-infinite trajectories, the trajectories that start from minus infinity, time minus infinity to time plus infinity, in which there's no blank, the blank symbol does not appear. They're exactly the periodic, the valid tilings of the original tiles. In particular, if the tile set is aperiodic, so these trajectories which do not have blank tiles, blank symbols, are non-periodic. Okay, so that was the second ingredient. So now the last ingredient, and this is beautiful observation, or okay, you can call it a theorem or observation or whatever. Yeah, so by Domani and Kinzel, and namely that if I have a probabilistic cellular automaton which has positive transition probabilities, all transitions have positive probabilities. It doesn't matter how small they are as long as they are positive. Now, if I look at an infinite trajectory of this probabilistic cellular automaton, so that means that by infinite Markov process. So this, the distribution of this by infinite trajectory is a Gibbs measure for an associated interaction, finite range interaction. So there is, if you give me a probabilistic, the local rule of a probabilistic cellular automaton, I can give you a finite range interaction, and which has this property that the by infinite trajectories, the distribution of by infinite trajectories are Gibbs measures for this associated interaction. The converse is also almost true. So Goldstein, Kauk, Lebowitz, and Miles, they prove that if we have a Gibbs measures for this associated interaction, which is shift invariant, then that is the distribution of a trajectory. But unfortunately, we don't know if this is true, if the Gibbs measure is not translation invariant. But anyways, I only need the first part, the observation by Domani and Kinzel. Okay, now we have all the 3 ingredients. We just put them together. And now, if I was successful in explaining to you what were the ingredients, it should be clear what we do. I mean, just my contribution to this was just to put these ingredients together. So in other words, so we start with Ammon's aperiodic tile sets, right, set of bank tiles. Then we extend it to a one-dimensional cellular automaton by adding this blank symbol. Now we use this idea of Thum, Gatch, and Raff to simulate it with a 3-dimensional cellular automaton, which is resistant against noise by stacking symbols. Now, then we add small symmetric noise to get a positive rate probabilistic cellular automaton. Now we have a probabilistic cellular automaton in 3 dimensions. So if I look at the the 3 space dimensions together with the time dimension, you know that if I consider the distribution of these trajectories, these are Gibbs measures for a certain interaction. Now the theorem would be that for this model, for this 4-dimensional finite range interaction, the configurations that are the clones of the Ammons non-periodic tilings, and that means that they are non-periodic, that they are validizing in 2 directions and constant in the other 2 directions, are strongly stable at positive temperature. Let me just give you some remarks. I'm almost done. So do I have more time or should I stop here?
Well, a few minutes are fine. So if you want to say something more, yeah, you can go.
Okay. Yeah. So first of all, I didn't talk about noise. Sorry, I didn't talk about temperature. So you can imagine that the way that I constructed was the temperature was 1. But now for this model, if I with temperature 1, if I lower the temperature, so if I vary the temperature, there is correspondence between the temperature and the level of noise, the intensity of noise. And there's just it's a nonlinear correspondence, but for any temperature corresponds to a level of noise. So if the temperature is low, that would correspond to low noise and vice versa. So this model also admits Gibbs measures which corresponds to immature tilings. So the tilings in which at some point we start to have blank. And that's not, it's not nice that we have those, but we have those. And in particular, the all blank configuration, if the configuration which is completely blank, that's stable at positive temperature. There might also be other Gibbs measures, but in general, it's very difficult to fully characterize the Gibbs measures of a lattice gas model, even for simple cases. Okay, so here are some open questions. I think for these particular constructions, the main question is how to get rid of those non-crystalline phases. And of course, there are all questions like how we can, whether it is possible to construct a model in 2 dimensions. That would be very interesting. Okay, so that is the end of my presentation. Thank you very much for your attention.
Thank you very much. Okay, so we have time for questions.
So,
Ayman, you want to ask?
So maybe I have some naive questions. So first of all, is there some analytical formulation of the ingredients you described to us? So
well, these ingredients are mostly combinatorial in nature.
So is there some function that describes them, or this is simply by induction? I don't know.
I'm not sure if I understand what.
I mean,
so for example,
we understand the examples, but is there some universal way to describe what is happening? I mean, by effort?
Yeah. So these are, like I said, they are combinatorial. So if you want to describe them, you essentially you have to specify an algorithm. But in this case, in simple examples, the algorithm is very simple. So you just have to, for example, in the case of in this example, so you just have to say what is the rule. And the rule, in simple cases, you can just say it in words, but there's nothing analytic about it, which, yeah.
Okay, and you talk about stability.
Yeah.
The measures. How stability is understood? In what sense? I mean.
Well, okay, so you have to formulate this exactly. So the way that I consider is that a ground configuration I consider as stable, as strongly stable, if at all sufficiently low temperatures there is a Gibbs measure which is essentially perturbation of that configuration. And the perturbation, by perturbation, I mean that almost surely we have the sea island picture. So almost everywhere we have agreement to the ground configuration, except for finite islands of defects, or finite islands of faults.
Okay. And the temperature is a parameter here. That's
Yeah, absolutely. Yeah, so that's the parameter.
Douglas?
Yes, hello, thank you. Sorry if I missed this, but did you describe the connection between the 2D and the 4D model?
So let me, the 2D, so you mean at the end, for the
You said they have a correspondence between 2D, or you increase with 2 dimensions, or the D,
okay, so
2 plus D.
right. So the way that the reason that we went from 2 to 4 was because of this simulation result, that if I have here, so if I have a d-dimensional, so in particular, if I have a one-dimensional cellular automaton, we can simulate it by a three-dimensional cellular automaton. And the idea is that we just replicate every symbol with a plane that has copies of that symbol. So there are 2 extra dimensions, and I copy them. And then there is of course, then I have to tell you what is the transition rule of this new cellular automaton, which has two extra dimensions. Mm-hmm. And this is the transition rule. So first I apply the Toombs rule, so the majority, this asymmetric majority in each of these planes. That would be my error correction. And then I apply in the original D dimensions, I apply the original cellular automaton. And now the idea is that if this is resistant, this is stable against noise.
Thank you.
Thank you for the question.
More questions? Okay, I do have a curiosity actually, but I don't know whether it's even a question, but maybe I'll ask anyway. So, can you say anything about the decay of correlation functions? There is no decay, right? So because there is no, well, or there is no decay rather, sorry. So you cannot reformulate your long range order in terms of decay. Am I right? Or?
No, I think, yeah, so there are some results for this, for Toombs model that, but then we cannot directly apply that. So you have to do some work. So as far as I understand, I understand the decay would be exponential. So if you look,
okay.
Yeah.
Okay. Mm-hmm. Yeah, because exactly there is no long range order in the usual sense. So there is no translation along long range order. So it's, I think you would never observe something like that. Okay. That makes sense. Okay, I think we can. So there are any other questions? If not, I think we can thank our speaker again. So thank you very much. So let me reminder for all the speakers. We would like to ask you to leave the slides, or to leave us the slides to put them on the website. It's time. So it's a real pleasure to introduce